quick run through some of these early parts of the book that you may not have had a good look at. So physics is all about these physical quantities and measuring physical quantities. We use a standardized set of units so that all the formulas work, and it's called the System International. It comes from French, that's why the adjective's at the end instead of at the front. It's based off the metric system because the French were the first to come up with the metric system. Bit of glare, I don't know if I can get rid of it, but anyway. So these are the System International units. Right, 7 fundamental units of the System International: length, mass, time, current, temperature, amount of substance, and luminous intensity. Everything else can be worked out by multiplying these things together in different ratios. So length, of course, is measured in the meter, meters, kilograms, seconds, amps, Kelvin, mole, and look, we don't even do luminous intensity, candelas. Moles, in high school physics, we don't really look at moles either. You look at that more in chemistry. Kelvin is the one for temperature though, so that's interesting. Kelvin, of course, is the same size as Celsius, but you start at negative 273, that's 0 Kelvin. The prefixes, we use them already. You probably just don't even realize, like centimeter is 100th of a meter. Deci means a tenth. Kilo is 1,000. So you've been using them your whole life, but there's some that you won't have come across before. And most of the time we're in this range here from micro up to mega. Nano is used in waves, nanometers. Wavelength of light is in nanometers. So from nano through to mega, sometimes giga, is the area that we're mainly interested in. Right, so I said before we had those 7 fundamental, they're called base units as well. All of these other units that are given here as examples are derived units. They come from combinations of the other thing. So acceleration is measured in meters per second, so it's meters and seconds. There are ways of deriving all of them using the others. Right. When you need to convert units, so say you have got, 6.3 by 10, 6.3, yeah, that'll do, by 10 to the 2 kilometers, and you need it in meters. So let's go over here. 6.3 by 10 to the 2 kilometers, and you need it in meters. You're about to get confused. If you replace the prefix with what it stands for, so kilo is 1,000, so that's by 10 to the 3 meters, then it's 6.3 by 10 to the 5 meters. Right, so replace that with whatever it stands for. So if it was 6.3 by 10 to the 2 millimeters, then you'd have 6.3 by 10 to the 2 by, milli is 1,000th, so 10 to the negative 3 meters. So that's 6.3 by 10 to the negative 1 meters. Right, you need to know your index rules. So that's an easy way to do it without getting confused. That's how I sort of do it in my head. Right, significant figures. There's a whole list of rules here. They're also on the handout that I've given you. The idea is that once you start putting an estimate into your measurement, there is no point in recording a dozen decimal places in the end. So there's some rules there. Significant figures were important in the old syllabus. They're very minor in the new syllabus. Some rules for multiplying and dividing and how you round them. So with multiplying and dividing, you look at which has got the smallest number of significant figures that you're working with. So this one has only got 3, so your answer would only have 3. This one has only got 2 significant figures, so you're only going to give 2 significant figures in your answer. And if you change to scientific notation, it makes the number of significant figures obvious, because in 1560, I know the 1, 5 and 6 are significant, but I don't know about the 0. If I write it in scientific notation, I can make sure that it's obvious. If I put the 0 on there still, then yes, that 0 counts. But in this case, we only needed 3, so I wouldn't count the 0. Same with this one. I can't tell whether the 1, 5 and the 0 are significant, but when it's written in this format, I can see that it's only the 1 and the 5. Errors and error analysis. So, systematic error comes from your measuring instruments or your measuring technique, and it is consistent. So those that cause readings to deviate from the accepted value by consistent amount. If you're looking at a graph, you will find that should go through 0, 0. If it's not, then that's a sign of your systematic error. So common causes: not zeroing or calibrating the instrument that you're using to start off with. The actual, calibrating something. So pH meters and things have a calibration fluid that you have to use. Parallax error occurs when you do not stand directly in front of the needle. Like when you're in the passenger seat and you think someone's speeding, but they're not because of the angle you're viewing the needle. And lots of these kinds of scales actually have a little strip of mirror there, so that you stand right in front and the needle and the image have to line up to know that you are in the right position, to try and get rid of parallax error. Right, reaction time is there as well. Environmental causes, could be environment, could be air resistance if you're dropping something to work out gravity. Oh, here we go. Here's the graph scenario where it should have gone through 0, 0 because it's current and voltage. So when there's no voltage, there's no current. It should go through 0, 0, but it's not. So that shows you the y-intercept, gives you the systematic error. Right, if you are taking a measurement, like say you're measuring the length of something, and you are only doing it once, then you record the uncertainty as half of the smallest scale division. Same if it's an electronic digital scale. It's half of the smallest scale division. That's if you're only recording it once. For the majority of our experiments, what we do is we record a number of trials. Right? So we record for a single measurement, you're going to record half the scale value. That's all spelt out here on page 20. So it's best estimate. The absolute uncertainty is half the scale, and you have your units. So that's straightforward. But once we are doing multiple measurements, so it doesn't have repeated single readings. Once you're doing multiple measurements, which is what we do most of the time, then you're going to be using that uncertainty formula. So the maximum reading minus the minimum divided by 2 to get the uncertainty. All right, you can also use standard deviation, but I never learnt to do that, so we're not going to do that. The syllabus just asks that you record it in an accepted way, so this is an accepted way. Now, when you're going to do your student experiment and you're going to be making some calculations, you're going to have to propagate or carry forward the uncertainties. So absolute and percentage uncertainty. So absolute uncertainty is this one that we did back here. This gives us the absolute. Absolute is just a numerical value. Percentage then puts the absolute uncertainty over the measurement, like we do when we have the graph one and we've got the slope plus or minus whatever to get the percentage uncertainty. And you use them for different things. There's a little caution down the bottom of the page on page 22 about temperatures. So your Celsius would have to be in Kelvin before you did anything with it. This little bit here is going to be important for your student experiment. So if you're just adding and subtracting, you use the absolute uncertainties. As soon as you start multiplying and dividing, you need percentage uncertainties. The bulk of your calculations will involve multiplication and division, so you would have to be using percentage uncertainty. So that just means that you get the uncertainty, put it over the mean, and multiply by 100% to get the percentage uncertainty. And then, confusingly, error is a measurement of your measure against the accepted value. So absolute error, again, is just a numerical value, so the observed minus the accepted, which is the one you've looked up somewhere. And then if you put that over the accepted value, multiply by 100, you've got the percentage error. That'll do for this bit, I think.